Good afternoon, everyone. My name is Apurva, and I am one of the conveners for today's webinar. Well, first of all, I would like to welcome everyone to the meeting today, and especially Dr. Phukan, who has joined us all the way from United Kingdom. Well, before moving to the technicalities, I would like to give a very brief idea on why we wanted to organize this webinar series. Well, the Department of Physics, DK College and Kamrup College thought that we would create a platform where we will provide an opportunity to all the young students from our state to interact with the researchers. Actually, we thought that all the researchers were involved in cutting-edge research. If they inspired the students of Assam, it would be a very great idea. So we thought that our idea will be very much well received by all the students of Assam, and we urge the students from Assam to make the best use of this opportunity. So with that hope, now I would like to hand over the proceedings to my friend Himanshu, who will be introducing the speaker to all of us and carry the meeting forward. So over to you, Himanshu.
Thank you, Apurva. So we consider ourselves really lucky that Dr. Phukon agreed to deliver this talk on such short notice. And yeah, so thank you so much. Anyway, Dr. Phukon completed his undergraduate studies from Cotton College and his master's from Guwahati University. He then obtained his PhD from IIT Kanpur. He was part of the LIGO collaboration that was awarded the Nobel Prize in Physics in 2017. We are, of course, excited to hear more about it in the talk. He then moved to Amsterdam for a postdoctoral position at NICHEF and University of Amsterdam. Thereafter, he was briefly at University of Utrecht, I hope I pronounced that right, and is now at the University of Birmingham, UK. So we hope participants have an amazing time today, and of course, I'd like to mention that participants can interact with him in both English and Assamese. So over to you, Dr. Phukon. You're muted. Can you please unmute yourself?
Okay. Thank you. Thank you very much. Yeah, sorry for this technical issues here. Yeah, good afternoon, everyone. Yeah, thanks for the nice introduction, nice and warm introduction. So I'm Khun Phukon, and so I'm working as a postdoc here in Birmingham, and so today I'm very happy to talk about gravitational wave astronomy, which is the newest branch of observed astronomy. So actually, this branch has started just 5 years back. Yeah. So today, actually, I'm going to talk about observation of compact binary mergers. And I'll be kind of I'll focus on results from LIGO Virgo's past 3 observation. So basically, I'll try to present things in the bilingual mood, so that we'll have more interaction with the students. So I request students to ask anything. You can also stop me in between a talk. So basically, in Assamese, it will the title of the talk would be. Title of the talk is Mohakorkhaniya Toranga Jyoti Bigyan, Hongkipto Jugmotorar Ekotrikaran Ba Hongokor Nirikhan. Jugmotoram means binary star, and so Hongkipto may not be right translation of compact, but yeah. So Hongkipto means compact means compact objects are actually end product of star. So I mean, when the massive stars die and form black holes or neutron stars, those objects are called compact objects. So here in LIGO Virgo, we observe collisions of compact binary mergers through gravitational waves. And yeah, so I also for my sincere thanks to Dakshin Kamrup College and Kamrup College for organizing this event called Podata Bigyanar 80 to our Bodo. Thanks. Okay, let's start. Yeah, so actually the story started with observation of this object in 2015 by LIGO Vargo collaboration. So this is animation of the events we observe by this SXX collaboration, and basically they simulate these collaborations simulate black holes, collision of black holes or neutron stars, and so so the here what you are seeing, the two black holes, they are approaching each other, and finally they're merging and forming one stable black hole. And during the process they emit gravitational waves, and this collision happened almost 1.3 billion years ago. That means 30 কোটি বছর. And so here mass of one black hole is 36 times more than mass of sun. The second black hole is 20 times heavier than sun, and during this process they emit energy. They emitted away 3 solar mass, energy of equivalent to 3 solar mass, and finally they form a black hole whose mass is 62. And so before going to details, let's talk about history of this branch of science. So we all know Newtonian gravity is a very very much successful in describing almost everything we see. But there were some limitations. In 1915, Albert Einstein put forward general relativity, which was a revolutionary idea back that time. And so it describes gravity as an effect of curvature of space-time. So when one famous scientist, Wheeler, he summed up general relativity as using this line. So he told that space-time tells matter how to move, and matter tells space-time how to curve. Basically, general relativity describes these things. And so using this simple equation, you can describe general relativity. But although it looks simple, but it's very complicated and it's very difficult to solve. I mean, you need huge supercomputers to solve these equations. Of course, one can have some approximate solutions. So 1 year after formulation of general relativity, in 1916, Albert Einstein predicted existence of gravitational waves, but he was unsure that whether it will be detected in future or not. It will be detected in future or not. So so what are gravitational waves? So gravitational waves are basically, Einstein put forward the concept of space-time, and general relativity are kind of ripples of the space-time. So the ripples are created by huge energetic events which may disturb the space-time, and this disturbance propagate from one corner to other corner of the universe. So these are just like waves of water surface, just for kind of visualization. So in 1960, experimental effort to detect gravitational wave had started. So Zeb Weaver from University of Maryland pioneered that effort. And in fact, he claimed detection of gravitational waves using bar detectors. So these are some kind of bar-shaped detectors. But even he wrote some papers, but later it was, So those are actually kind of false detection because there are some issues with the analysis of data. So in 1960, Rainer Weiss, he proposed the idea of using interferometers, which students will, I think students will be using interferometers in their experiments in DSc or MSc classes, laboratory classes. So in 1960, Weiss proposed the idea of using laser interferometer to detect gravitational waves. And in 1980s, the construction of interferometer started in US and Europe, basically in Italy. And the US detector is called, detectors are called as LIGO. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And the European and named their detector after Virgo cluster. And so, and later LIGO scientific and Virgo LIGO scientific collaboration and Virgo collaboration are formed. So because well, to analyze to extract science from this kind of instrument, you need huge scientific team. And so the LIGO scientific collaboration has almost more than 1,200 members and more than 100 participating institutes from 18 countries. And same with, I think, same with the Virgo. Virgo has more 650 members, 100 institutions, and 14 countries. So yeah, these kind of big science experiments kind of unify a world. So in so LIGO started observation from 2015, and Virgo started observation from 2017. And in the first month of LIGO's observation, we observed one gravitational wave signal, and since then LIGO Virgo have observed almost 100 compact binary merger detections in 3 observing runs. Okay, so basically what we try to measure, so we try to measure effect of passing gravitational wave. So suppose this is a cylinder, and through the cylinder we have one passing gravitational wave. So when gravitational wave passes through something, it distorts the space. So you see here in one direction it is stressing, and one direction it is squeezing. So that means we'll have some sense of length. And so since gravitational waves are extremely weak, so for a kilometer size of detectors, the detectable length change would be 1,000 times smaller than size of a proton. So we try to observe this quantity h, which is del L by L, differential length change, and this is a periodic thing because of the quasi periodicity of the gravitational wave signals. I'm sorry. And so in principle, almost anyone can produce gravitational wave, but for detectable gravitational wave, we need some of the extreme objects of universe. So different kind of gravitational wave observatory are proposed. So currently the terrestrial interferometer, that means Earth-based interferometers, are working, and LIGO and Virgo, these are the kilometer size long terrestrial interferometers. And so these detectors are sensitive to compact binaries composed of neutron star, black holes. So these are actually stellar mass black hole. I mean, their masses would be similar to Sun or slightly higher than mass of Sun. And space-based interferometers are also proposed, and these detectors will be sensitive in the low frequency regime. That means they will target for kind of supermassive black holes. And we have also another kind of window to observe gravitational wave, which is pulsar timing arrays. That is observation of pulsars using radio telescopes. And when so gravitational wave will leave some nice pattern in the pulsar timing observation. And there are different pulsar timing observatories working in this world, arrays basically. So in India also we have one pulsar timing array. And gravitational wave will also have imprint on cosmic microwave background radiation, which are kind of some of the earliest electromagnetic signals of the universe. So here in this talk, we are mostly focusing on observation of LIGO Virgo or terrestrial detectors, and we observe mergers of neutron stars or black holes. And so this is just here I'm showing a picture of the LIGO laser interferometers, and it's the main components are basically the laser, the beam splitter, and 2 mirrors and 1 photo detector. And you can see it is much more complex in reality, which is the layout of the interferometer is shown in the right figure. Yeah, so I'm going to this simulation, and I collected from LIGO. Okay. So when gravitational wave passes through something, it changes length. So here, what will happen if gravitational wave passes through this detector? Then one length of one arm would be longer than the other arm. So which is and if this happen, what you will see the light beam will be will constructively interfere, and we can collect signal in the photo detector. If the length of the 2 arms remain same, then we'll not see anything in the photo detector. So we'll see a signal only when gravitational wave change the length of detectors, and because of length change, we'll see in constructive interference, and we'll get some signal. So currently, currently the operating gravitational detectors are using this basic technology. We have 3 or 4 operating detectors at this moment. 2 in US, they are LIGO Hanford and LIGO Livingston, and their arms are those arms are almost 4 kilometers long in these 2 detectors. And in Virgo detector, which is in Italy, the arm lengths are 3 kilometers. The Japanese have also one detector which is underground, and the arm lengths are 3 kilometers. And in coming years, we'll have one detector in India. So I hope in the next decade or next so LIGO India will be operational. And these detectors are sensitive in between few hertz to few kilohertz. And using these interferometric detectors, we expect to see 4 kind of sources. The coalescing compact binaries, which I'll be talking about about in this talk. And the transient bar sources. Transient sources means supernovae. And stochastic background, these are produced by some cosmological processes. And continuous sources, I mean spinning neutron stars, they emit continuous gravitational wave. The continuous sources have will be immediate. They will not have too many frequency components. These signals will be immediate at a fixed frequency. And the other signals will have kind of broadband nature. They will cover a range of frequencies. Okay, please, if you have any questions, please let me know. I'm happy to take questions and answer. Sorry?
So if you have any question, participants can either type it in the chat box or unmute yourself and okay, I see a hand. Yes, please go ahead. Okay, please feel free to ask the question in any language you wish. Okay.
Yeah, অসমীয়াটো শুনিব পৰা কোনো কথা নাই, মানে গম পাইছো কেতিয়াবা অকমান শংকা আহি যায়। You can ask anything. চিন্তা কৰিব নালাগে।
So if not, I would like to ask a question actually. Can I go back to the previous slide?
Yeah.
Yeah. So no, the next one. Yeah. So the what I see around the Virgo detectors are actually like, are those actually fields where cultivation is done?
Yeah. So there are some fields. Yeah.
So during the actual observational runs, so do they stop the cultivation or what? Because it's too noisy.
No, I'm not sure if they stop, but I don't know how much ground vibration those farming activities can create. So, but LIGO Virgo have kind of good mirror suspension, and they can cancel lots of
the seismic noise isolation is I think too good to be affected by the farming activities, right?
Mm-hmm.
Yeah, okay. So Himanshu, maybe I want to put two questions to the speaker. So that might be a very rookie kind of a question. So you said that in order to detect this gravitational wave, we have this interferometer kind of arrangement.
Mm-hmm.
So so can we think of something other technology by which we can detect this gravitational wave, or is it this is this the only method by which we can detect it?
Right now, kind of this is the only effect, because people try to detect gravitational wave using bar detectors. Okay, but bar detectors are kind of very narrow band detectors, and they are not so they are not that effective. And like this interferometer pattern is setup is useful because, see, I mean, if you see sorry. If you see the animation, you can see, I mean,
yes.
Suppose you are so you can see, come on. You can see the effect of passing gravitational wave. It will keep on changing length in both sides.
Yes.
So that's why interferometer are very useful in detecting this kind of effect.
Okay, fine. And one more question. Like you said about our Indian effort for detecting gravitational waves. I think it's named something like Indigo or something like that. So
Indigo is the name of the consortium. Yeah.
Okay, okay, fine. So, when do you think it will start operating? Because I have been hearing about it since I was very much young. So,
Mm.
like, do you think that in the next decade it will start gathering the data? And what is the status of the construction? Like, how far has it reached?
So far, what I know, this LIGO India Scientific Collaboration, they have acquired the land. That's a huge piece of land, 4 by 4 kilometer, and they started doing some construction, some activities like uh, construction of vacuum system, because you need to put the whole system in vacuum, so you need 4 kilometer long vacuum system. So this kind of activities are going on, and India has signed some agreement with US counterpart, because US had 3 detectors, and components from one detector will be shipped to India. So some MOUs has been signed, that I know. And of course, in India, we have sometimes we have funding issue, and currently I think we are facing those issues. And hopefully in next decade we'll have these detectors running.
Okay, fine, fine. Thank you. So
Okay,
I
we
think,
have two
yeah.
questions in the chat box. Yeah, yeah.
Yes.
So near he's asked, can we resemble G waves with EM waves? If yes, does a planet's magnetic field affect the G waves coming from black holes?
No. So they are very different from electromagnetic waves, and gravitational wave weakly interact with anything. So that means it's very unlike well, so it's very unlikely to distort gravitational wave by something. So in electromagnetic signal, you can just block electromagnetic signal using kind of walls, some kind of wall of some kind of material. But gravitational wave can't be blocked, so they will travel from one end of the universe to the other end. So that's why these signals are very interesting. I mean, you can probe the space much deeper than what EM signal can do.
Okay, there's a follow-up question from him. Why do G waves not interact with others? Is their wavelength so large?
Yeah, that's true. Wavelengths are very large. Yeah.
Okay, we have another question from Lipon Jyoti. I hope, yeah. Why only Kagra has built underground while others are built on the ground, above the ground? Yeah.
Okay. Okay. First of all, you need lots of money to build something, put something underground. And Japan actually, well, Japan in Japan, they had already one setup, because they put detectors here in a mine. They already have this kind of setup, called pre-existing setup. And in Japan, I think land is also one issue. But the future generation detectors will be underground detector, because the future generation detector will have arm length close to 10 kilometer long long arms. And because of Earth curvature effect, you can't put such a long detectors above ground. So the future detectors, that means those are actually there'll be two future these kind of detectors. One will be in Europe, that is called Einstein telescope. Then the other one will be in US, which is called Cosmic Explorer. They will have kind of 10 to 40 kilometer long arms, and those detectors will be put underground. And one advantage of putting things underground is that you can reduce these things, seismic noise, some sort of
Okay, is the seismic isolation better if we put it below the ground?
no, you will have lesser surface vibration, and also those detectors will be cryogenic. That means you will have much better control over some noise fluctuations.
Okay. So next, Parthapratim Sharma. So what kind of waves are the G waves, sir, if they are neither mechanical nor EM waves?
Okay. GM waves is difficult to. Okay, so we know we are living in a space-time. So and gravitational waves are basically some perturbation so in the space-time, in the space. So for example, we are living on a space-time, so it's and GW are basically just some fluctuation ripples, and we can feel passing gravitational waves effect. So they will cause change of length between objects, and those changes are very small. They are kind of 1,000 times smaller than, so for 1 kilometer size object, that change of these lengths would be 1,000 times smaller than size of a proton. Yeah, so
Okay, so maybe we can take the questions later on and go ahead a little forward. Right?
okay. Yeah, so far we have detected compact binary mergers, and so they have characteristic gravitational, they emit characteristic gravitational wave signals. So the compact binary mergers, so their orbit gradually shrinks. The orbit gradually shrinks, and at some point they merge, and after some and the merger is followed by the ring-down phase, where they would form one. The two merging black holes would form one single black holes. So this process is kind of a very much relativistic process. The relative velocity between two objects reaches almost close to half of the velocity of light. And so that means gravitational wave provide a direct way to probe a very high relativistic regime. And so here in this cartoon, you'll see that two black holes orbiting around each other. They are characterized by masses and spins, and the chi1, chi2 are just projection of spins on the orbital angular momentum. So these signals have kind of a chirping kind of behavior. That means the amplitude and frequency keep on increasing as they approach towards each other. And so these are kind of rate of detections in the detections done in last three observations, last three observing run that started in 2015, from 2015 to 2020. So here you see in the first observation, the one we detected only 3 events. In O2, second observing run, we have 8 detections. And in O3, O3 was divided in 2 parts, O3A, O3B, and we have almost 79 detections. And in total, we have 90 observations of compact binary mergers that include binary black hole, binary neutron star, and black hole neutron star objects. And here in the figure, masses in stellar gravity figure. So main we are showing. I'm showing masses of objects of observed by LIGO-FIGO detectors, and So the blue points are compact objects observed by LIGO-Virgo detectors. Sorry, black holes observed by LIGO-Virgo detectors. And yellow ones are neutron stars observed by LIGO-Virgo detectors. And the others are observation from electromagnetic signals. So the main takeaway from this plot is that through gravitational wave, we are observing a totally new population of compact binary objects, which is very exciting because those part of parameter space were not accessible by electromagnetic signals. And so we have detections, and we also want to give name to each detections and how we name them. So we name after the day of observation of that event. So GW 15-9-14, which is observed on 14 September 2015, was the first detection of gravitational waves. And so two LIGO detectors observed that event, and it was that merger of these two objects happened almost 400 megaparsecs away from us, which is 1.3 billion year light travel time. And here you can see a time frequency map of the observed signal. Here you have a clear chart pattern. That means the frequency and amplitude are increasing, keep on increasing as they approach each other. And here in the zigzag, the curves represent the observed signal and some of the predicted signal. The zigzag noisy curves are signals observed in the two detectors, LIGO-Hanford and LIGO-Virgo, and the clearer curves are the models, predicted model. Predicted signal. Okay, so yeah, so we so for detection of this kind of event, we need huge computational power and very robust methods, and we usually use Bayesian analysis framework and to observe to estimate properties, to extract properties from these kind of events. And these are detected by LIGO and Virgo detectors, and between the two detectors, the light travel time was 6.9 milliseconds. To confirm detection, we need detection of these kind of events in multiple detectors. So that's why, and that detection of these events by LIGO and Virgo kind of shows how detection by these two LIGO and Livingston were important to confirm this event. Here actually this signal was transferred to the audio band, and you will see the sound. It is the chirping sound because it is because the gravitational wave is kind of analogous to sound wave, because in sound wave you have a change of because here you have periodic change of length, and in sound wave also you have some change of pressure. And you can hear this can be easily transferred to audio band, and this is the sound of this event. And another important observation from this LIGO Virgo's first observing run is second observing run is GW 17-08-17, which is the first binary neutron star observed, and this is followed by some this binary neutron star is also associated with short gamma ray bursts and and with this observation, the multi-messenger astronomy has started. And because multi-messenger means observing the same object through defined observing window, be it Gravitational wave, electromagnetic waves, or particle physics new experiments. So after merger, there was short gamma ray burst, and the short gamma ray burst was observed by different in EM telescopes, and these are followed by kilonovae and defined afterglows, and those were also observed by radio telescopes. And this event had huge impact on us. This event enabled different kind of science. For example, Hubble constant measurement, is nuclear astrophysics, studying nuclear physics using this event, and many things. And in 03, one interesting event is 190521, which is the most massive object we have observed so far, and this hint of formation of intermediate mass black holes from stellar. Before that we never knew existence of this kind of black hole of this mass. And we have also two interesting events. One is 1904 14 and 1904 to 12. These are kind of similar in a sense. Their mass, the two components of the binary are very asymmetric. One is very heavy, very massive. The other one is very light, and these kind of objects have high order multiple, and this enables better measurement of distance, which is very important to do astrophysics, astronomy. And another interesting event is 1904-25, which is considered as a binary neutron star, and this shows existence of a new kind of neutron star populations. Here in this figure, you can see existing neutron star population. That dotted line shows by galactic binary neutron stars which were observed so far, and the yellow and blue line represents masses observed from this event, and this shows that this shows existence of a new kind of neutron stars in universe. So okay, so now I'm just going to summarize what science we did from this kind of observations. So gravitational wave observations enabled studying general relativity. Here you can see constraint on we define constraint of deviation from general relativity, and we also put constraint on masses of graviton. Gravitational wave observation also enabled relativistic astrophysics. Here in this figure, in the disk plot, you can see a measurement of spins, and spin is a truly relativistic phenomena. And gravitational wave also allowed us to do cosmology. So it allows us to measure Hubble constants using a very independent way. It also allowed us to study evolution of compact binary mergers rate, and gravitational with the detection of first binary transistor, we are formally in the era of multi-messenger astronomy, and so this observation also allowed us to do nuclear physics using astrophysical sources, studying nuclear synthesis. That means so basically synthesis of heavy elements in the universe, and of course Hubble constant measurement, and different kind of transient astrophysics. And LIGO-Virgo's observation also enabled gravitational wave science, and it releases LIGO-Virgo regularly release data and public data, and different groups also do and did analysis on these data, and they also did different kind of sorry gravitational wave astrophysics, and now gravitational wave data are regularly used by much wider community. And yeah, so I'm coming to conclusion. So we basically gravitational wave astronomy has just started, and I think future is very promising and bright, and we'll have more observations. O4 is scheduled to start sometime April next year. I think April next year, and Kagra will join O4, which is the Japanese detector. LIGO India is scheduled to join observation in O5. I don't know when O5 will start, and the international community is also planning for third generation detector like Cosmic Explorer, Einstein telescopes, and they can probe the space much deeper. But there will be also space-based detector, LISA, and Chinese are also planning another space-based detector, and there is another window to observe gravitational wave as well, which is pulsar timing array. Pulsar timing are regularly observing sky to detect gravitational wave. Yeah, so yeah, I conclude my talk here, and thank you very much for the invitation. Yeah, please let me know if you have any questions.
Yeah, participants, you may please go ahead and ask your questions. অসমীয়াত সুধিলে ভাল হম কোনে অসমীয়াত সোধা নাই তাকে
Hello,
anything related? Yeah, sure.
Khun
Please go ahead.
It's Devabrat from Obeyapuri College. So I have a few questions to you. Like you said, okay, ma Ohamiate কৈছো তেন্তে the students বিলাকে বুজি পায় যে Hubble expansion rate to আপুনি measure কৰিব পাৰিব বুলি কৈছে by observing gravitational wave. So I mean এটো মানে process to কেনেকুৱা হ'ব যে মানে by the time when it reaches earth যে আমি gravitational wave signal to কিমানখিনি expand হল তাৰ wavelength to তেনেকুৱা কিবা measurement হ'ব নেকি? Like we measure the wavelength expansion in the cosmic CMBR তেনেকুৱা হ'ব নেকি?
No, Hubble constant measurement to ইয়াত কি হয় দুটা ইস্যু থাকে, redshift measurement, distance measurement. So gravitational waveৰ জৰিয়তে কোনো ধৰণৰ systematic error নথকাকৈ distance measure কৰিব পাৰি, আৰু কিবা কিবি আৰু বিভিন্ন ধৰণৰ statistical method use কৰি redshift measure কৰিব পাৰি, আৰু তাৰ পৰা সেই মেজাৰমেন্টৰ পৰাই Hubble constant to measure কৰা হয় সাধাৰণতে।
Okay. So currently there is a tension in the Hubble expansion rate measurement, like the cosmological and astrophysical measurement. So they don't match. So
yeah.
Probably.
Right. So gravitational wave Hubble constant measurement value kind of 68, আৰু 68 to cosmological আৰু CMB measurement আৰু মাজতে পৰিছে মানে।
Okay.
ইম্প্ৰুভ হ'ব, আৰু আৰু যিটো বাইনাৰী নিউট্ৰেন্সৰ অবজাৰভেশ্যন ইয়াত আকৌ কি হ'ল অলৰেডি আমি গ্ৰেভিটেশ্যন ৱেভৰ পৰা সুন্দৰভাৱে ডিষ্টেঞ্চটো পাওঁৱেই কোনো হেৰি নোহোৱাকৈ কাৰণ গ্ৰেভিটেশ্যন ৱেভৰ যিটো সিগনেল ষ্ট্ৰেংথ এম্প্লিটিউড ইনভাৰ্সলি প্ৰপৰ্চনেল টু ডিষ্টেঞ্চ তাৰ পৰা সহজতে ডিষ্টেঞ্চটো কম্পিউট কৰিব পৰা যায়
ওকে
বাকি এষ্ট্ৰফিজিকেল মেজাৰমেণ্টটো যিটো লেডাৰ চিষ্টেম তেনেকুৱা ধৰণৰ নকৰে জানো ভুল হোৱা সম্ভাৱনা থাকে ইয়াত ভুল নোহোৱাকৈ কম মেজাৰ কৰিব পাৰি আৰু এই নিউট্ৰন ষ্টাৰ মেজাৰমেণ্টত কি হয় ইয়াৰ লগত যিটো ইলেক্ট্ৰমেগনেটিক সিগনেল ওলাই তাৰ পৰা ৰেড চিপটো মেজাৰ কৰিব পৰা যায় কাৰণ তাত গেলাক্সি ক'ত আছে কি আছে এইবোৰ ধুনীয়াকৈ ক'ব পাৰি আৰু এই মেজাৰমেণ্টৰ পৰা হাবল কনষ্টেণ্টটো মেজাৰ কৰা হৈছিল আৰু তোমাৰ এই ফিগাৰটোত এটা প্লেংক মেজাৰমেণ্ট আৰু চুজ এইটো চাগে চুপাৰনোভা মেজাৰমেণ্ট নেকি মষ্ট প্ৰবেবলি আৰু যিটো গ্ৰেভিটেশ্যন মেজাৰমেণ্ট ধুনীয়াকৈ মেজাৰমেণ্টৰ পষ্টিৰৰ মাজত দুইটা আহি গৈছে
ওকে আৰু মানে গ্ৰেভিটেশ্যনেল ৱেভ মই শুনিছিলো যে গ্ৰেভিটেশ্যনেল ৱেভ যিটো আমি বাইনাৰী চিষ্টেম যিটো আমি ডিটেক্ট কৰি আছো সেইটো আমি এক্সাক্টলি পিন পইণ্ট কৰিব পৰা নাই বিকজ অফ lack of another detector, another art-based detector. So, সেইটো মানে এতিয়াও ইস্যুটো এতিয়াও still exist. I mean, we are not able to detect the exact pinpoint, the point in the space, no?
Yes, মানে কি হয় গ্ৰেভিটেশ্যন ৱেভ ডিটেক্টৰবোৰ মানে omni directional, সকলো ফালে sensitive. আৰু লোকেশনটো মেজাৰ কৰিবলৈ হলে কি হয় যে টাইমিং মেজাৰমেণ্টৰ পৰা মোটামুটি লোকেশন মেজাৰমেণ্টটো কৰা হয় আৰু যাৰ ফলত মানে এটা হিউজ পেচ পোৱা যায় অলমোষ্ট ইম্পচিবল পিন পইণ্ট কিন্তু আৰু হৰভাগ ডিটেক্টৰ এটা সমস্যা আছে কি আটাইবোৰ নৰ্দাৰ্ণ হেমিস্ফিয়াৰ আছে এই যদি ফিগাৰটো চোৱা লাইগো ভাৰ্গো কাগ্ৰা অলমোষ্ট অল আৰ ইন নৰ্দাৰ্ণ হেমিস্ফিয়াৰ চ' এটা ডিটেক্টৰ যদি সাউদাৰ্ণ হেমিস্ফিয়াৰত থাকে লাইগোটো যেনেকৈ সাউদাৰ্ণ হেমিস্ফিয়াৰ হ'বই কিন্তু তেতিয়া সেই লোকেলাইজেশ্যনটো ইম্প্ৰুভ হ'ব কাৰণ টাইমিং ইনফৰমেশ্যন যদি বহুত ডিটেক্টৰে লয় মানে যিটো মানে ট্ৰাইংগুলেশ্যন চিষ্টেম তোমাৰ আগতে জাহাজ এখন পিন পইণ্ট কৰিবলৈ ট্ৰাইংগুলেশ্যনটো কৰে বহুতে সেই ট্ৰাইংগুলেশ্যন ইম্প্ৰুভ হ'ব আৰু ডিটেক্টৰ
Okay, one last question. এইটো মানে আমি মই বেসিক্যালি পাৰ্টিকেল ফিজিক্সত কাম কৰি আছো সো পাৰ্টিকেল ফিজিচিষ্ট বিলাকে মানে হাউ হোপফুল শুড উই বি about this gravitational wave astronomy কি মানে এইটো আমাক আপোনাৰ CMB-ৰ আগৰ ইনফৰমেশন আই মিন দিব পাৰিব মানে ইন প্ৰিন্সিপল দিব পাৰিব So I mean, in the near future, মানে আমি কিমান মান টাইম স্কেল এটা ভাবিব পাৰো যে এনেকুৱা ইনফৰমেশন আমি GW ৰ পৰা পাম আৰু
ওকে মানে যদি আমি হেল্প CMB টাইম স্কেলৰ পিছলৈ যাওঁ কি হ'ব আমি কি আশা কৰিম ষ্টকিষ্টিক বেকগ্ৰাউণ্ড গ্ৰেভিটেশ্যন ৱেভ সিগনেল চ' কাইণ্ডলি লাইগো ভাৰ্গৰ ডিটেক্টৰে ডেটা পোৱা মানুহ যিটো ষ্টকিষ্টিক ৱৰ্কিং গ্ৰুপ তেওঁলোকে চেষ্টা কৰি আছে ডিটেক্ট কৰিবৰ কাৰণে কিন্তু নট ইনাফ চেনচিটিভ এতিয়ালৈকে আৰু মেবি হয়তো O5 মানত এটা টাইট আপাৰ লিমিট দিব পাৰিব কিন্তু গোটেই প্ৰচেছটো আই থিংক ডিপেণ্ড কৰিব কিমান হাই কোৱালিটিৰ ডেটা আমি পাওঁ আৰু চাগে যিটো নেক্সট জেনেৰেশ্যন ডিটেক্টৰ তাত ডেফিনেটলি ডিটেক্ট কৰিব পৰা যাব চাগে এই ষ্টকিষ্টিক বেকগ্ৰাউণ্ড মানে আৰ্লি ইউনিভাৰ্ছ প্ৰচেছৰ ছিগনেলছবোৰ
Okay, thank you.
Okay, anyone else? If not, more এটা question আছিলে actually. আপুনি যিটো এটা intermediate mass black hole detection কথা কৈছিলে এইটো okay. So এইটো যে লেন্স সিগনেল নহয় মানে কেতিয়াবা গ্ৰেভিটেশনাল লেন্সিঙৰ কাৰণে আমাৰ ৱেভফৰ্মবোৰ অকমান খেলিমেলি হৈ গলেও ইন্টাৰমিডিয়েট বুলি ভাবিব পাৰো সো হেতু মানে কিমান ৰাইগৰাছলি অফ কোৰ্স ৰাইগৰাছলি তেওঁলোকে ষ্টেটিষ্টিকেল এনালাইসিস কৰিছিল চাগে বাট কেনেকে এই পসিবিলিটি ৰুল আউট কৰিলে
একচুয়ালি খুব সম্ভৱ মানে লেন্সিং সিগনেল যদি চাবলৈ হলে কেইবাটাও এস্পেক্ট চোৱা যায় আৰু এটা এস্পেক্ট হৈছে একেটা ডাইৰেকশ্যনত সোৰ্সটো আছে নে নাই মানে গ্ৰেভিটেশনাল ৱেভ লেন্সিঙে সিমান বেছি লোকেশনটো চেঞ্জ নকৰিব নহয় জানো কিন্তু মাছ প্যাৰামিটাৰ মানে সিগনেলটো এম্প্লিফাই হৈ পিনিও ডিফাইন বেলেগ মাছ হ'ব আৰু মেবি টাইম দিলে হ'ব যাৰ ফলত এটা বেলেগ সময় ডিটেকশন হ'ব যদি লেন্স হৈছে
একেটা ৱেভফৰ্ম মানে বেলেগ
আকৌ বেলেগ সময় দিছো কিন্তু তেনেকুৱা একো সিগনেচাৰ নাপালে এই সোৰ্সটোৰ লগত
Okay. So ultimately মানে ইন্টাৰমিডিয়েট মাছ ব্ল্যাক হোল বুলি কনক্লুড কৰিলে
মানে যেটো ফৰ্মেশন হৈছে ফাইনাল ব্ল্যাক হোলটো হেতু 142 সোলাৰ মাছ এটো মানে মোটামুটি ইন্টাৰমিডিয়েট মাছ ৰেঞ্জত পৰে আৰু ইয়াৰ প্ৰাইমাৰী ব্ল্যাক হোলটো মাছ 85 66 সেকেন্ডাৰী আৰু ইহঁতৰ মাছখিনি যথেষ্ট হাই যেটো সটল পিছন মাছ গেপ বুলি কয় পালসেটিং সামথিং মই পাহৰি গৈছো সাধাৰণ যেটো ষ্টেলাৰ ইভলিউশন তেওঁলোকে প্ৰেডিক্ট নকৰে ফৰ্মেশন অফ ব্ল্যাক হোল উইথ দিস মাছ আৰু এই মানে সোৰ্সটোৱে যেটো আমাৰ এক্সিস্টিং ষ্টেলাৰ ইভলিউশন মডেল তেওঁলোকক মানে মোটামুটি চ্যালেঞ্জ কৰিছে
okay
কাৰণ ইমান হেভি ব্ল্যাক হোল ফৰ্মেশন টু মানে বহুত ফৰ্মেশন বহুত ইভলিউশন মানে ফৰবিডেন আৰু যথেষ্ট পেপাৰ লিখা হৈছে এষ্ট্ৰফিজিক্যাল কিন্তু মই ইমান ভালকৈ পঢ়া নাই বাৰু কাৰণ
okay
আৰু এটো বহুতে ছুটি সিগনেল
টাইমটো যথেষ্ট
তিনটা সাইকেল আছে আৰু টাইমটো দেখি few seconds yeah
Okay. So Himanshu, I want to ask a question actually. So Dr. Phukan, so apni olop agote kole je gravitational waves also gives evidence of spin যেটো relativistic effect হয় so হেতু আপনি অলপ briefly কব পাৰিব নেকি যে how does it do that
how does
যেটো স্পিনৰ কথা কলে আপনি লাষ্ট এখন স্লাইডত কলে যে it also has some evidence of spin in it so হেতু মই অলপ জানিব বিচাৰিছিলো মানে how does it give us the evidence of spin
okay extra evidence আপোনাৰ কি হয় okay signal to now we can model okay because using post-Newtonian approximation to general relativity আৰু Newtonian relativity numerical relativity use কৰি মানে আমি gravitational wave signal বোৰ মডেল কৰিব পাৰো আৰু যেতিয়া সাধাৰণতে কোনো স্পিন নাথাকে মানে প্ৰিসিজিং স্পিন বেসিক্যালি
okay
প্ৰিসিজিং বুলি কোৱা লগে লগে যেতিয়া স্পিন এলাইন হৈ নাথাকে এতিয়া in this cartoon spin to align along with orbital angular momentum কিন্তু যেতিয়া এলাইন হৈ নাথাকে তেতিয়া প্ৰসেস হয় মানে প্ৰসেস হোৱাৰ লগে লগে ইয়াৰ অৰবিটটো ফিক্স হৈ নাথাকে অৰবিটটো মুভ কৰিব অৰবিটটো যিকোনো অৰিয়েন্টেশন হ'ব আৰু যাৰ ফলত আমি এনেকুৱা আমি ক্লিন সিগনেল দেখা নাপাম আমি দেখা পাম সিগনেল য'ত মানে বিভিন্ন এক্সট্ৰা মডুলেশন থাকিব
okay
আৰু স্পিনে তেনেকুৱা ক্যাৰেক্টাৰিস্টিক কিছুমান মডুলেশন এৰি যায় সিগনেলটোৰ ওপৰত আৰু এই স্পিন কনস্ট্ৰেইন বা মেজারমেন্ট খুবই ডিফিকাল্ট LIGO ভাবে অবজারভেশন বাট উই হ্যাভ সাম হিন্ট but বহুত টাইট মেজারমেন্ট but ক্লিন মেজারমেন্ট বা টাইট is difficult because আমাক আৰু সেনসিটিভ ডিটেক্টৰ দৰকাৰ
okay fine thank you
participants সকলৰ পৰা যদি আৰু কিবা question পাব পৰা যায় especially the young participants, and or anything related to today's lecture or maybe your career or whatever.
Career,
Yeah, you can interact. In fact, hey, the opportunity best use going parle. It's our objective actually. So please go ahead, participants.
Okay, মই তেনেহলে অকমান সৰুৰাকে কেৰিয়াৰ পাৰ্সপেক্টিভ হ'ব পাৰো মানে সাধাৰণতে আমাৰ এটা ধাৰণা যে PhD কৰিলে শিক্ষকতা বা ৰিসাৰ্চ তাতেই মানুহৰ কেৰিয়াৰ কিন্তু এতিয়া এইবোৰ মানে আৰু বেলেগ ধৰণৰ কেৰিয়াৰ কিছুমানো থাকে কাৰণ আজিকালি কাৰণ সাধাৰণতে গ্ৰেভিটেশ্যন ৱেভ সাবজেক্টবোৰ বা এষ্ট্ৰনমি আজিকালি খুবেই মাল্টিডিসিপ্লিনাৰী যাৰ ফলত not only physics তোমাৰ এটা প্ৰগ্ৰামিং কৰাৰ ধুনীয়া ক্ষমতা এটা আহি যায় বা যিকোনো বস্তু সুন্দৰভাৱে এনালাইজ কৰা আৰু আজিকালি এইবোৰ ডমেইনত মেচিন লাৰ্নিং পৰা আৰম্ভ কৰি বিভিন্ন ধৰণৰ টেকনিক ব্যৱহাৰ কৰা হয় যাৰ ফলত এটা সময়ৰ পিছত তোমাক খুবেই স্কিল কৰি তোলে আৰু যাৰ ফলত মোটামুটি জব মাৰ্কেটত খুবেই ডিমান্ডিং হৈ যায় আমাৰ এতিয়া ইণ্ডিয়াতো ধৰা তেনেদৰে মই বহুত মানে PhD স্কলাৰক বিভিন্ন কোম্পানীয়ে হায়াৰ কৰে দেখিছো এইটো এটা ডাঙৰ কেৰিয়াৰ প্ৰস্পেক্ট ৰিসাৰ্চ আৰু টিচিঙৰ বাহিৰে আৰু কেনেকৈ ষ্টাৰ্ট কৰিব পৰা যায় এইবোৰ এতিয়া কি হয় আমাৰ ইণ্ডিয়াত কিছুমান ইনষ্টিটিউট আছে তেওঁলোকে সামাৰ ষ্টুডেণ্ট লয় MSc ষ্টুডেণ্ট বা BSc ষ্টুডেণ্টবোৰে যদি সামাৰ ব্ৰেক এটা পায় তেতিয়া যাব পাৰে আৰু আই থিংক কিছুমান ফেলোশ্বিপো থাকে আৰু সেইবোৰে যথেষ্ট কামতো সহায় কৰে নিজৰ CVখন ভাল কৰাত মানে পিছলৈ যিকোনো জেগাত PhD বা কিবা সেইবোৰ কাৰণে এপ্লাই কৰিবলৈ সুবিধা হয় তেনেকুৱা যদি ফেলোশ্বিপ এটা পোৱা যায় যেনে ইণ্ডিয়ান একাডেমি অফ সায়েন্স তেওঁলোকে সামাৰ ফেলোশ্বিপ ৰেগুলাৰলি দিয়ে মই আৰু এটা স্লাইড বনাব পাৰিলো এদিন সৰি বাৰু ICTS বেংগলৰ তেওঁলোকে কিছুমান ফেলোশ্বিপ এনাউন্স কৰে সামাৰ ষ্টুডেণ্টৰ কাৰণে কিন্তু অকণমান আগতীয়াকৈ এপ্লাই কৰিব লাগে ধৰা নেক্সট সামাৰৰ কাৰণে হয়তো এই ডিচেম্বৰতে এপ্লাই কৰিব লাগিব
Indian Academy of Sciences to probably এতিয়াও খোলা আছে নেকি
থাকিব পাৰে
যদি চাই এপ্লাই কৰিব পাৰিব So participants, please go ahead. If you don't have any question, we'll end the session soon. So, Prabhupada, yeah, you have anything to say?
I think it was a very good interaction with the speaker. I mean, আমি expect কৰিছিলো যে student বিলাকে আৰু কিবা কিবি question সোধক, but anyway, it's a starting for them. Maybe in the future talks that we organize, we will expect more questions from the participants. And mostly, I think we could learn a lot from it. Even personally, মই নিজে বহুত বস্তু মানে কিছুমান শিকিলো যিটো মোৰ আগতে মোৰ knowledge নাছিলে in fact. So, Dr. Phukan, a big thank you to you. And I think that's it. I mean, I think we can now probably end the session with a vote of thanks. What do you say, Himanshu?
Yeah, yes, we can. So, personally also, তেখেতক যথেষ্ট ধন্যবাদ জনাইছো in a very short notice talk to কাৰণে agree কৰিলে actually.
Yes.
Informally আমি approach কৰিছিলো আৰু our actually talker plan to যথেষ্ট sudden আছিল বুলি ক'ব লাগিব but still it happened, so thank you for that. So formally maybe we can proceed to the vote of thanks session.
Yeah, okay, fine. So finally, I would like to offer my vote of thanks, especially to the speaker, Dr. Phukon, who took out his time from his busy schedule to deliver the talk today. So it was really an exciting talk, and I got to learn a lot from it actually I could learn, in fact, a lot of details about the gravitational waves, and I also hope that students could also learn a lot from it. And finally, I would also like to thank the HODs from both the departments and all the faculty members of Department of Physics, DK College and Kamrup College, for the effort that they have put in to make today's meeting a successful one. And also, I must also thank all the participants for attending the talk today. So I hope that in future you will support us like the way you did us today. So we'll continue to meet again for the next meetings as well. So with that, I conclude. Okay, so over to you, Himanshu.
Okay, so thank you so much, Apurvada. So maybe we can declare the end of this session. So
yeah, and probably you can maybe tell the participants like
Yeah.
about the certificate details and all, whatever you want to say.
Yes. So that has to be done. So the rule was that there will be a series of talks, maybe 5, 6, 7, or we'll continue on a particular theme. And today's theme was astronomy and astrophysics. So that there will be around 5 or 6 talks. And if you attend at least 3 talks, you will receive a certificate of participation from us. But and that will be done by you'll get a feedback form, right, Apurvada?
Yes, we'll send a feedback form. Probably,
Yes.
yeah.
And which will confirm your registration and participation. So that's it. So hope to see you soon. We'll announce the date of the next talk very soon. We are contacting the resource person, the speaker. And the participants who have registered for the first talk, they do not need to register in the second for the upcoming talks. You have already joined the WhatsApp group, so you will be notified there. But the feedback form you'll have to fill up for all the sessions. So that was from my side.
Okay, so Dr. Phukan, thank you once again. So maybe concluding remarks, you want to put in something?
No, I mean, well, thank you very much. I really enjoyed talking to you. Also, I enjoyed talking about GW. And best wishes to this program.
Thank you. So we'll keep on contacting you even in future. Maybe you can enlighten our students as well in the future. So anyway, a big thank you to all of you.
Yeah, thank you very much.
Okay, so finally, okay, we'll conclude now.
Okay, bye-bye.